absence of dependent failures. So what does this dependent failure mean? It comprises of two parts. One is the absence of common cause failures. So a common cause failure could be something like a clock failure or a voltage failure. So a common cause, as the word easily explains, it is caused by a common problem. So it could be that there is an EMC issue or there is an voltage issue that is affecting multiple elements. So when multiple elements are affected by a single root cause, then those are called as common cause failures. So we need to understand what common cause failure is. And then the other aspect of dependent failures is the absence of cascading failures. Cascading. So again, as the word cascading tells us, cascading means that a problem caused in one element is cascading, or it kind of goes from one element to the other. So that is what is called as a cascading failure. So the cascading failure, it's also referred to as the property of freedom from interference, FFI. So Sridhar, if you can go to the next slide, please. So whenever we are talking about freedom from interference, what this means is that all the ECUs, or most of the ECUs that we are having, they are mixed ASIL systems. What a mixed ASIL system means is that it is not going to be that the ECU contains all the software that is of a particular ASIL level. It could be of multiple ASIL levels. ASIL B and ASIL D could coexist, or it could be that QM and ASIL could coexist. And so here the property of freedom from interference is to ensure that a QM software or a lower ASIL software does not affect anything on a higher level ASIL software. So that is what freedom from interference is all about. Now, when we talk about freedom from interference, the standard talks about three possible ways in which interference could happen. One is timing and execution, the other is memory, and the third aspect is exchange of information or communication. So freedom from interference should be ensured in all these three aspects. If you can go to the next slide, please, Sridhar. So when it comes to freedom from interference in the timing and execution aspect, first thing that we need to understand is what can potentially go wrong when we talk about timing and execution. So maybe we are using a single core microcontroller, and so there are some QM tasks and ASIL tasks that are running in the same core. In such a scenario, there is the possibility that your QM task could block the execution of your ASIL task, or your system could enter into a deadlock or a live lock, or you could have done something incorrectly, or during the running, the execution time allocation is not correct. So there could be problems arising because of that. And there is also the possibility that the synchronization between the software elements is incorrect, due to which there are issues in the QM task and the ASIL task. So this is the problem statement when it comes to timing and execution. Now, there are multiple ways in which this could be avoided. The most commonly used way is what is called as an alive monitoring. So here in this particular system, what you do is you basically try to see, okay, how do I ensure that my safety critical task is always active and active in a particular amount of time. So that is what is alive monitoring. There is as well one another aspect called deadline monitoring, and the most complex one is the timing protection unit. So a timing protection unit is a feature that could be available in your operating system that we could use to avoid the problem coming out of timing and execution. Again, we are not going to go into the details, because what we are trying to, as I said in the introduction, what we are trying to do here in this session is to give you a flavor, an overview of what the concepts are and how to think on when you're starting to think about creating a technical safety concept. How do you start thinking about what are the aspects? So that is what we are going to be talking about. So definitely there would be other future sessions in which we can dwell into each of these items in depth. But for today, it's going to be a high level overview. Next slide, please, Sridhar. Yeah, so the next aspect is freedom from interference in memory. Now, here, the possible ways in which the potential issues can happen is, again, uh, between your QM software and your Acell software, your memory regions are shared. So it could be the ROM memory, it could be the RAM memory, even the non-volatile memory or the E-square PROM. All these could be shared between your QM and your Acell. And so in such a thing, what are the possible issues that could happen? One of the issues is that a QM software could incorrectly write into an Acell memory area, which could potentially lead to a safety goal violation. So corruption of content could happen. Then there is the possibility that the data is not consistent, so it keeps changing. So that's a problem. Then we are using stacks, so the stack could get overwritten, so a possibility of stack overflow or underflow could happen. And then finally, the biggest issue is that you have set access permissions, but still there are problems by which the read write access is incorrectly taken up by a component that should not have the access. So these are the potential problems that could happen when it comes to memory. And the ways in which this could be avoided is, again, the most common way I would say is the memory protection unit. And in some of the microcontrollers, they are called as the memory management unit. And the simplest way is to use redundant storage. But again, there are, obviously, when I talk about the potential ways, all of these mechanisms have their own pros and cons. So whenever we are deciding on a particular mechanism, we need to really understand what is the advantage of using a particular method and what is the disadvantage. So that would be covered separately. We'll go to the next slide, Sridhar. Yeah, finally, the third aspect when it comes to freedom from interference is the exchange of information or communication. So here we are talking about having a sender and a receiver. So a sender and a receiver could be between ECUs, between microcontrollers, or between components, software components itself. So the potential issues that could happen is that a data could get repeated, a data could be lost, somebody could incorrectly insert an information, or the order in which the data is sent is not the order in which the data is received. So incorrect sequencing, corruption of information. And then we are also starting to see cybersecurity coming into picture in the automotive world. And so there is the possibility that somebody could masquerade as a particular ECU. So somebody thinks, acts as though he's an engine ECU and sends you a command. So that's masquerading. And then the access to a channel could be blocked, or if it's a data that is broadcasted to multiple receivers, there is also the possibility that some of the receivers are not able to receive that data. So these are the potential issues that could happen. And some of the ways in which this could be mitigated are you could monitor the message. So basically, when we say monitor the message could be made periodic, and we could monitor whether there is a particular amount of time for which message has not been received. And then we have the end-to-end protection. So basically having alive counters and sequence counters, those could be possible. And then finally, when it comes to masquerading, we could always encrypt and decrypt the data so that only the valid receivers will be able to receive the data. So this finally wraps up the freedom from interference. So just to quickly wrap up, three aspects when it comes to freedom from interference. One is timing and execution, the second is memory, and the third is exchange of information or communication. So this is one aspect of that we need to consider when we are talking about deriving a technical safety concept. Can we go to the next one, please? Yeah. The next important thing when it comes to functional safety is the failure in time. So here we are talking about the hardware aspects. So we need to consider, okay, for different ASIL levels, there could be different hardware metrics. So there are three different hardware metrics that we need to consider. One is failure in time. So basically, this is the number of failures that can be expected in 1 billion hours of operation. So when somebody says that their system should have 100 fit, it means that their system can only take 100 failures in 10 power 9 hours of operation. The second aspect is the single point fault metric. So this is nothing but the number of single point faults that are controlled in our system. So when we say controlled, it is by design or by safety measures, you are able to avoid those problems from happening. So here as well, the standard specifies what are the targets. And then the third aspect is the latent point fault metric. Uh, um, the third aspect is the latent point fault metric, where we are talking about avoiding multi-point faults, dual point faults from becoming a safety goal violation. So I'll not go into the values that are there. Maybe we can go to the next slide, please, Sweta. Yeah. So now we talked about the hardware metrics, but why is that important for the technical safety concept? It becomes very critical because even though the critical point is that it is an indicator of the reliability of the product, but it significantly impacts the safety mechanism that you need to pick. So the higher the SL level, more the diagnostic coverage, the higher or the more stringent the hardware metrics that we need to achieve. And so it essentially determines what is the amount of safety mechanism that you're going to have in your system. And obviously, the more safety mechanisms you're going to have, it's going to have an impact in your cost and as well in the development effort. So that is how the hardware metrics gets tied to the technical safety concepts. So basically, higher the SL level, more the safety mechanisms that you need to have. Next slide, please, Sridhar. And finally, so basically, whenever I talk about freedom from interference, FFI, failure in time, and fault tolerant time interval, I call it as the 3 Fs of safety. Just for a quick understanding, I call it as the 3 Fs of functional safety, because if you understand these 3 Fs, you're almost good in understanding the basic concepts of functional safety. So the third F is the fault tolerant time interval, the FTTI. So basically, FTTI, you can consider this on a very, very high level. To make it very, very simple, it's the response time your system is allowed. So basically, the FTTI is the time from which the fault occurs to the hazard happening. So what is the time till which the fault remains a fault? It does not turn into a hazard. So this is the time by which you need to do something to ensure that your system cannot do something incorrect. So if you go to the next slide, please, Sridhar. So what becomes important is that we have what is called as the fault handling time interval. So obviously, the fault tolerant time interval is the time from fault to the occurrence of the hazard. And so the fault handling time interval is going to be lesser, smaller than the FTTI. And so this is the time by which the system needs to act and move your system to a safe state. So again, this FHTI is broken down into two parts. One is the time to detect the fault, because you need to confirm, because you should not end up, acting on some spurious problematic input. So you need to ensure that you debounce your failure for your fault for a sufficient time. And then once you confirm, you need some time to move your system to a safe state. So your fault handling time interval is the combination of your time to detect the fault and the time to transition to a safe state. So that becomes your FHTI, and this obviously will have to be lesser than the FTTI. Next slide, please, Sridhar. So finally, we come to the last but not the least of the concepts. So this one is about the Acell decomposition. So This is something that you will come across very frequently when we are talking about functional safety. And so what this gives us, I would say this Acell decomposition is kind of a tailoring or a method by which requirements could be broken down into redundant requirements, and then this could then be allocated to independent elements. So the standard itself provides us with various schemas by which you could do Acell decomposition. And the Acell decomposition could be done at multiple levels. It could be done at the vehicle level. So wherein one of the ECUs could become Acell, the OEM might allocate a safety requirement to one of the ECUs and make the other ECU as not being Acell compliant. Or it could be done at ECU level, wherein if you are using a multi-micro solution, then you could have certain micros having Acell requirements and certain micros not having Acell requirements. So that is at the ECU level. And then finally, you could as well do it at the hardware or the software level. So if you look at the CAN stack and the E2E, alive counter or checksum, that again is a decomposition that is done at the software level. So the Acell decomposition, just to reiterate, is a method by which you could simplify the requirements that you are allocating to your components. Again, when we are, again, I know that I'm simplifying Acell decomposition so much, but there are definitely certain terms and conditions. There are certain requirements that needs to be met when we are talking about Acell decomposition, but that's a separate story. So we'll talk about it later, but just understand that this makes our system and our life simpler when we do the Acell decomposition. Yeah, I think with that, so with this, so now with this, I've given all the inputs that are required for the understanding the key aspects of functional safety. Now we really jump into the inputs that are required for creating a technical safety concept. So the technical safety concept, it takes basically the inputs from functional requirements. So finally, your system has to meet some functional requirements. You cannot just have just safety mechanisms in your system. So you need to have functional requirements. So that is the key input. Then you need to look at what is your system architecture. Whatever Soumya presented earlier, that is a key input that we need to have for creating a TSC or a TSR. And then we need to look at these safety manuals, the safety manuals of your microcontroller or maybe your various peripherals that you are using in your system. You need to consider that. Then the data sheets, because the data sheet is a treasure trove of information where it has so much information about what is the what are the features that are provided in that peripheral or in that micro. So the data sheet should be consulted, and then obviously we need to consider the freedom from interference, the independence, timing requirements. When we say timing requirements, that could be the FTTI requirements, or that could be requirements driven by your system. So you need to consider those. And then the hardware metrics, the FIT, the SPFM, the LFM. So these needs to be considered. And then finally, last but not the least, we need to look at the manufacturing process, because the functional safety is an end-to-end aspect. So it does not start and stop at the system level or at the software level. It goes all the way till the manufacturing as well. So you need to think, okay, how is my ECU going to be manufactured? How do I test that my ECU is exactly matching what I intended to go about doing? So all that things should be considered. So that is where we are bringing in the inputs, that manufacturing process. Yeah. So these are the inputs that we need to consider. Now, before we even jump in and start creating the TSC or the TSR, the most important thing that we need to do is we need to do a safety analysis on our system. So that is where I'll hand over to Sridhar. Over to you, Sridhar. Thanks.
Thank you, Nagesh, and thank you, Soumya, for giving the defining the system safety architecture, and then thank you, Nagesh, for bringing up those important aspects of functional safety to consider in technical safety concept. And yeah, the main aim for the functional safety is to reduce the hidden failures. So Nagesh explained some aspects of failures, like freedom from interference and other things. So similarly, safety analysis is also one another way of identifying the failure modes for the elements which we used in our system. So we integrate multiple elements to form our system to meet the requirements. So we need to analyze those failure modes, whether that impacts my functionality, my safety related functionality, and what is the measure I need to take to ensure those failure modes are addressed. So here we have two methodologies, and ISO 26262 recommends both FMEA and FTA. Based on the Acell level, FMEA is a standard approach for all the Acell levels, and FTA is mainly recommended for Acell C and D. It didn't mean that we don't need to perform FTA. If needed, still we can use it FTA as well. So let us start with FMEA. It's failure mode effect analysis. So it is going to identify the safety hazards in a product. So it is going to identify the failure modes which impacts my safety related hazards. And FMEA is a widely used approach, and we can use it on a system level, subsystem level, hardware component level, software component level, process level, even other industries as well, using like a chemical industry, or anybody can use FMEA for the to get some measures on it. So it's a widely used methodology, and our ISO 26262 as well recommends this to perform the safety analysis. So here we'll be using this at system level and also at the hardware component level. So the aim of FMEA here is to analyze at only system level. The steps for the FMEA is common for all these phases. So first we need to have we need to understand the scope of our analysis. So we need to have some diagram which explains about the system boundary, so which we will be getting from the system architecture which Soumya explained. And then we need to list down what are all the functions or requirements we have in our system. And then we need to analyze those failure modes. So we can go ahead with the functions own failure modes, or we can go ahead with guide words. So this is something widely used, and this gives as well a good coverage. So like guide words, no function, partial function, sporadic function, unintended function, and unacceptable side effects. So this can be as well used as a failure modes to assess the effect. And next we need to assess the effect. And then till this is a FMEA. And for the criticality analysis, we need to consider the severity of the failure mode, severity of the effect, occurrence, and detection. Based on that, we need to assess the risk priority number. So that gives the criteria. So which failure mode to be treated with high priority. And then we need to identify the measure. We need to track for closure. And we need to repeat this. So FMEA is not a single time activity. It has to be repeated iteratively. So we take measures, we revisit the FMEA, and we'll revise the RPN number. Then we need to look for the same criteria. So in this, which Soumya explained, the system architecture. So if we look at here, so the main function we have here is the status or indication on the LCD display, and the indication on the LED indicator to the driver. And then we do have other functions like power supply, CAN, ignition, clock, memory, and speaker. For the old product we have. And in that, except speaker, all other elements are contributing to functional safety. So if any one of the element got an error, that is going to impact our indication. So for example, if ignition is giving us a wrong input, it might impact the functionality. If CAN is providing a wrong input, maybe we'll be showing some unintended value. If my memory, like in the EEPROM, will be storing the calibratable data, which may be the feature related applicability, or my other parameters, if that got corrupted, that might also impact my display. So we need to consider first what are all the elements is used in our system, and then we need to identify the scope. So what are all the elements we need to analyze? So that gives the scope, and then that also gives us the requirements we need to analyze. So here we come up with a simple representation of FMEA. So our system is driver notification system, and then so the main just for time being, I've taken two main use cases. One is driver notification LED and driver notification TFT icon. And we applied the guide word. So we just mapped the guide word here: unintended function, partial function, sporadic function, no function, and unacceptable side effect. So unintended function is we have some we commanded some input, but the output is not as expected. So it is off when on, or it is on when off. And then partial function is something, some of the functions are working, the other functions are not working. So this is how we mapped what could be the example behavior for this guide word failure modes. So we took those failure modes and we analyzed any of this effect happens, it is going to violate our safety goal, because our expectation is to notify the status to the driver. And then we need to understand, analyze the cause of the failure. So the unintended function could be incorrect software implementation, or if we take sporadic function, that could be incorrect software scheduling. So these are all the cause of the failure. So what is the measure we need to identify? So if it is a LED related failure, we can implement a LED feedback monitoring, or if it is a scheduling related issue, we can have a health manager. So these are all the safety mechanisms which is coming from the failure modes and the effect we analyzed in FMEA. And this will as well one input to prepare the technical safety concept. I mean, to the detailed technical safety concept. Next is FTA, fault tree analysis. So we saw FMEA. Maybe I'll slowly compare that with FMEA first. What is FTA, and then we'll start the FTA. So FMEA we did. It's a bottom-up approach. We took all the failure mode and we all the way go up to identify the effect at system level. Wherein the FTA, it is a top-down approach. We first take the use case or the effect that as a top event, and then we go all the down to understand the final failure mode which started this. And basically in FMEA side, we know the failure causes and we'll assess the effect. In the FTA, we know the effect and we assess the failure causes. And FMEA is mainly will not distinguish it's a single point failure or multiple point failure, or even FMEA will not distinguish whether it is a common cause failures. But wherein in FTA, we can identify that, and even we have a tool set which is easily helps us to identify it. And FMEA mainly focuses on product level, where some of the failure modes might not violate our safety goal, but we still analyze as a product level. But FTA, where we started with use case level, and we'll mainly focus on that particular use case, what all the failure mode will results in that particular effect will be analyzed. So as I mentioned, the FTA focuses on the top event and what are all the failure modes which results in the top effect that will be analyzed. And it will also provides us a logical path from the lower level event. So what are all the my final event cost for the top event to occur? So that we can understand in both the things. And in FTA as well, so we need to understand the boundary, and then we need to define a top event, which is our main use case, and then we need to identify the objective. So what is my objective? Is it a qualitative to identify only measures, or it is a quantitative to understand the target metrics as well? And then we need to start building the tree. So basically the fault tree contains it's a graphical representation where everything will be graphical notations. We can see events, gates, and then we need to identify the measures. As it is a graphical representation, we need to document the analysis as a report. So it's the same diagram to understand the scope of the analysis. And here we just took one use case, which is loss of driver indication notification, which is our top event, and we need to assess those failure modes which results in the top event. So here I just marked it as some legends to understand how do we classify each and every notations. So you can refer this and you can understand in detail. Let me go to a specific use case to explain how we arrived at. So my top event is loss of driver indication notification. So one of the intermediate or one of the category is my processing side. There could be some fault. So the processing side might have some execution related fault, and it could be a blocked off execution. So basically it's a software stack is my failure mode, which results in my loss of driver identification notification. So I'll be adding Watchdog as a safety mechanism. So this is my first order of failure, and I added a safety mechanism. What if the safety mechanism failed? So that is my second order. For that, I'll be adding Watchdog self-test as a latent false. So still we can analyze this as well. What if the self-test get failed? So as a third order, if required, we can go till third order as per ISO26262. Otherwise, we mainly need a first order and second order to understand the failure modes and the safety mechanisms. So similarly, just to explain furthermore, for the LED feedback monitoring, so my LED fault becomes first order, and then we add a LED feedback monitoring. What if that feedback mechanism fails? We'll be adding a plausibility check to understand whether ADC peripheral is working fine. If that also fails, we can add a ADC self-test. What if the self-test fails? So this is how the final event will go. So now we also identified some of the safety mechanisms at a high level. So now Soumya will consolidate everything as a detailed technical safety concept.
Yeah, thank you, Sridhar. So I think before we go into the technical safety concept, the next stage of it, we will take a few questions. We have around 2 or 3 minutes of time where I think we can take some of the questions. So Nagesh, maybe do you want to take the question on, there's a question on Acell decomposition. The question is, why is that for the same product, different OEMs have different Acell decomposition? For some same product, few OEMs have Acell B of D and few OEMs would request C of D. Why is this so?
Interesting question. So that's a great question as well. So I think there are a couple of factors that go into this decision. So maybe there are some pre-existing systems that they have, which they have developed at, let's say, B, and so they want to decompose it that way because they could reuse at least one part of their system. So they already have, let's say, a B system. And so when they decompose D, they decompose it as B of D and B of D. So then they get to reuse that B of D, whatever they already used. So, and similarly, so somebody could have developed something as SLC. And so in such a scenario, they might do this. So that is one thing that I could immediately think of when I saw this question. Yeah.
Yeah, okay. Thank you, Nagesh. Then there is another question on the fit rate. So is it sufficient enough to call a system as Acell compliant if it reaches its target fit rate? I can take this question. So the very short answer would be no. And why no? Because Acell compliance is an aspect of two different things: systematic failures and random hardware failures. So we have a quantification of fit only for the random hardware failures of our system. But unfortunately, the ISO 26262 doesn't talk about quantification of the systematic faults that remain in our system after we've done the whole Acell development process. So the expectation as per the standard is for the random hardware failures, you would have to meet the target fit rate. And as you know, the target fit rate starts only from Acell B. So if you take an Acell A system, there is not even the target fit rate. It's not even mandatory unless an OEM wants you to do it. So in that case, for all the systems from Acell A to D, you would have to achieve the sufficient mitigation of the systematic failures. And to achieve the sufficient mitigation of the systematic failures, we would have to follow all the methods that are stated in the process according to the different SL levels, and the processes increase more and more as we go to the higher SL levels. So that is how we are taking more and more stringent measures to mitigate the systematic faults. So yeah, the answer would be that we would need to consider both the systematic fault mitigation as well as the mitigation of random hardware failures to call a system as SL compliant. Yeah, then there is another question. There are lots of questions coming in, but in the interest of time, we'll take one more and then we'll have to move to the other, the next part of the PPT. And one thing is that we'll make sure to come back to all of you with the answers of all the questions that have been asked. It's just that we are not having the time to answer all the questions here. How is the fit being distributed over the system? Nagesh or Sridhar, can one of you take this? Yeah, okay.
Yeah, it's a good question. Fit is basically will be calculated at system level. It's a consolidation of fit rate coming from the individual components. So we have a reliability analysis. So that helps us to identify the component level fit rate. And then we will be performing the FMEA analysis that will identify each and every component failures, whether we have safety mechanisms or not, and what is the diagnostic coverage for each and every safety mechanism we added, and what is the uncovered fault in both a single point fault metric side and latent point fault metric side. What is uncovered, that becomes my metric that will also used here to get what is the uncovered fit from the overall fit which we took from the reliability for our entire product. So what is the safety related uncovered fit? So this is first we consolidate all the fit rate based on the safety mechanisms we have, and then we will come up with what is the final fit rate for the product.
Yeah, thank you, Sridhar. I think let's continue the session, and we will we've noted the other questions that have come in as well, and we will try to answer them towards the end of the training or offline via a Q&A that we can post in LinkedIn. So yeah, this part of the session is about how we are now going to finalize the technical safety concept based on all the inputs that we have received. We've received an overview about what is freedom from interference, Acell decomposition. We've talked about safety analysis, FMEA, FDA, and so how does all of this come together, and how does it help us to finalize the technical safety concept? So next slide, please. The most important thing when it comes to the technical safety concept is to define the right safety mechanisms, to define sufficient safety mechanisms for that system. So for this, we need to consider mainly 4 aspects. The freedom from interference aspect that Nagesh described at a spatial level, that is at a memory level, at a timing level, and at a communication level. Then the mitigation of common cause faults, and what are the safety mechanisms to mitigate common cause faults. The third thing would be what are the outcomes from the safety analysis, the FMEA or the FDA, and how what are the safety mechanisms that are coming out of the safety analysis. And lastly, what is the hardware metrics that is required of our system, and would we need to have additional safety mechanisms to achieve the hardware metrics? Next slide, please, Sridhar. Okay, now let's come back to the same, the simple driver notification control system that we introduced you to. So in this system, if we talk about communication FFI safety mechanisms, here the main communication channel is the CAN. So for the CAN, one safety mechanism that can be introduced is the end-to-end protection safety mechanism, which is basically protecting the CAN messages using a CRC, using an alive or a sequence counter, and also timeout monitoring. And of course, there are further end-to-end aspects that are available in many standards, like in the AutoSAR standard, for example. But this would be the most important aspects of an end-to-end protection, which would be the CRC, the alive or sequence counter, and the timeout monitoring. So this would have to be implemented in the system to achieve the freedom from interference from a communication aspect. Next slide, please, Sridhar. Let's now come to the memory aspect. So from a memory aspect, to avoid interference, we would need to make sure that the QM software does not interfere in the memory of the safety software. So it shouldn't be able to access or write into the Acell software. So in this case, we have considered that this system has a memory protection unit, which is a widely used concept in many microcontrollers now to achieve spatial separation of softwares of different ASIL levels. So that would be a safety mechanism for achieving the FFI from a memory aspect. And additionally, we would have to think about stack overflow and underflow detection. As Nagesh mentioned, this is also an important failure mode that is coming out from the standard for memory interferences. So for this, we assume that the operating system in this case has a measure for detecting the stack overflow, underflow, and stack to prevent stack corruption issues. And lastly, we also have the external memory in our system, which is the EEPROM, NOR, and NAND flash. So we would have to think about how do we prevent a corruption of the, let's say, the safety-related content in the EEPROM or the external flash memory. So for which we will have to implement, let's say, a redundant buffer or a CRC or a checksum. There are many different methods that are given in the standard, but these would be some of the mechanisms that we will have to deploy in order to achieve FFI in the external memory. Next slide, please, Sridhar. Now, let's come to the third aspect of FFI, which is the temporal or the timing FFI. So for timing and execution, in this system, we have considered that the system has a health manager that is monitoring the aliveness and the periodicity of the safety tasks. So because we need some kind of a health monitoring to make sure that all the safety related tasks are being executed correctly. So this system has a health manager that helps us achieve the timing FFI. Then we also have an interrupt monitoring, because the system has a lot of peripherals like, let's say, CAN and ADC and GPIO, which would need interrupts. And if we have interrupts that are missing or not coming in the expected frequency, in case they are periodic interrupts, then this can lead to a violation of a safety goal. So we have considered that the system has an interrupt monitoring in place, and thereby the safety functionality is not affected because of interrupts being missed or being incorrect. Then the third aspect is the watchdog, because the watchdog is the one that is monitoring the overall process, all the software execution, and so it is going to save the system in case the safety software is not executed correctly, or if there is a stuck at fault in the execution, then the watchdog will save the day. So we would need to implement, let's say, a watchdog that is independent from the CPU clock in order to achieve the timing FFI. And the last aspect we have considered is we have considered that this OS has a rate monotonic scheduling, that is a fixed priority based scheduling, where the higher priority tasks run for a shorter time, and the lower priority tasks run for a relatively longer time. So thereby, there is a very, I would say, well-designed system where every task is running at a defined amount and periodicity that is predetermined carefully, and thereby interferences are prevented by a good design. So these are the safety mechanisms for the system from a timing FFI point of view. Next slide, please. Next, we come to common cause failures. So if you look at this diagram, it might be very easy to identify what are the common causes. There is a power supply, that is sourcing the entire system. So the failure of the power supply is a common cause fault. The memory can also be a common cause fault because let's say there is an EMI EMC issue or some kind of a let's say the memory loses power, whatever. These are common causes that affects multiple aspects. It can affect multiple safety goals. It can affect multiple functionalities. So it becomes a common cause, a source of common cause faults. And then we have the CPU on which the entire software is running. So this can be a common cause. So there are so many different common sources of common causes faults that are in the system. So here we have implemented the mechanisms for it. So the memory integrity checks that we actually described it also in the memory FFI slide, but this would also help us achieve or mitigate common cause faults in this system, that is the SM4. Then we have considered that the system has ECC, a single bit correction and 2-bit detection for its internal memories and caches. Then for the power supply, which is a common cause, which could be a common cause fault, there is a power supply monitoring that can detect over voltage and under voltage faults. Then the next one is the ADC. In this case, we've considered ADC as a possible source of a common cause fault because the ignition input comes via the ADC, and the ignition serves as an input for many functionalities in the system. I mean, the entire system is dependent on ignition. And also we have considered that the system has an LED feedback. As you can see, there's a red arrow from the physical LEDs back to ADC. So there's some kind of a LED feedback to let us know whether the LEDs are really on or off. And so if the ADC fails, that can be a common cause failure for that system. So we have considered an ADC plausibility check as a safety mechanism to detect the aliveness and the correct functioning of the ADC. Then the next is the CPU core self-test. As I mentioned, the CPU can be a possible common cause fault if there is a malfunction in the CPU. So we implement a self-test to check the correct functioning of the CPU. And the last is the clock supervision. To make sure that we can detect any oscillator errors, like if it's stopped or if it is having a jitter or going out of the required frequency. To detect such issues, we will have a clock monitoring. So one thing you might have noticed is that we will have these safety mechanisms implemented, some in software, some in hardware, or some has both hardware and software in the implementation of the safety mechanism. Next slide, please, Sridhar. Then here, this slide is talking about some of the safety mechanisms identified from the FMEA or the FDA, whatever was done for that system. So in this case, we have derived connecting to the FMEA FDA that Sridhar showed, there is the TFT fault monitoring safety mechanism that has been considered in the system, because we mentioned that we have safety goals to show images in the TFT. So to detect those faults, we would also need to detect if there are any faults in the TFT itself, like if it's the TFT is frozen, or if it's just not operating correctly, or if it's having a power supply failure, whatever that can be. So we would have to have a TFT fault monitoring. And one important thing to note is that This means that we choose also the right components that are giving us this kind of fault monitoring capabilities. So, of course, if the TFT doesn't provide us these kind of capabilities, then we would not be able to implement it, even if the FMEA or FDA says so. So, the right choice of components at a very beginning stage of the program would be very crucial. Then the next thing is that we have considered a CRC checker in this yeah, thank you. We've considered a CRC checker in this system, that there is a CRC checker to verify the correctness of the images of the whatever is rendered in the display. Then SM16 is the GPIO port monitoring. So since we have the GPIOs driving the LEDs, the ports that are driving the LEDs, we are implementing based on safety analysis. We identify that ports can have faults, and we need to monitor the ports by reading them back to detect any incorrectness or a corrupted port setting. So we have considered GPIO port monitoring as a result. The last one is the LED feedback monitoring. So here we need to detect any hardware faults that are in the LEDs, like open or short of the LEDs, for example. And so we need a LED feedback monitoring, which is done using the ADC. Yeah, next slide. Yeah, this slide is talking about diagnostic coverage. So since we talked about fit earlier, and we talked about hardware architectural metrics, so just a very simple explanation on what is diagnostic coverage. So let's take that there is a LED that has a total fit of, let's say, 10 fit, which means that to the total raw fit of the system, the LED contributes 10 fit to the total fit of the system. So now, if we have a safety, no, before we go to that, let's consider what are the failure modes that this can have. So let's say that can be an open or a short or a drift. So yeah, let's take the resistor. Sorry, not the LED. Let's take the resistor. The failure modes of the resistor can be that there is an open, there's a short, or there is a drift. So if now I have a safety mechanism that can detect open or short and does not detect drift, then it means that only some part of the failure modes, that is not all the failure modes are covered, but only the open and the short are covered. Now let's say if the open has a 50% contribution to the total faults, like if I consider let's say 100 faults of the resistor, 50% of them, or 50 faults are open faults, 40 faults are short faults, and 10 of them are drift. So now if I have a safety mechanism that detects open and short faults, then that means that I have covered 90% of the faults in the system of the resistor, but there is still a 10% of fault of the resistor that is not covered, which means that when I implement the safety mechanism, I bring down the 10 fit to a residual of 1 fit, because I would have covered 5 and 4 fit for the open and the short. So I would have reduced 9 fit by implementing a safety mechanism. So what would be left will be only 1 fit. So that is how the diagnostic coverage, the concept of diagnostic coverage is like, by implementing a safety mechanism, you are bringing down the fit of the system by covering failure modes. And this is how it works in principle. Now, why did we talk about diagnostic coverage here? Let's go over to the next slide. Yeah, so now we showed you several safety mechanisms for various reasons, right? We've shown 17 safety mechanisms in the system. Now, we need to also think about what is the diagnostic coverage provided by these safety mechanisms right at the stage of TSC, because this becomes an input when we do the FMEDA at the stage of the hardware. So, for example, the SM1, which is the E2E protection in our case, we have given a 90% diagnostic coverage to this safety mechanism in this case. This is based on what we have derived from the part 5 of the standard. And of course, actually, we have the part 5 says that you can give up to 99% diagnostic coverage for the E2E safety mechanism with the way we have described it here, with the different CRC and alive counter and the timeout monitoring, but we have given 90% only since we have not covered masquerading failure mode as part of this concept. So that's how we have taken the part 5 as an input to derive the diagnostic coverage. Similarly, we can also take the inputs from the part 11 of the standard on semiconductors to derive the diagnostic coverage of a safety mechanism. And in some cases, the diagnostic coverage may not be an important aspect. Like, for example, the memory protection unit. This is purely a safety mechanism that is covering for software freedom from interference. This is not for random hardware failures. So in this case, we don't need to think about the diagnostic coverage of this safety mechanism. That's why you would see that there is a not applicable there. So similarly, we have derived the diagnostic coverage here for the different safety mechanisms. So you can take a look at this in detail after this session. Next slide, please. Okay, so now this is a final consolidated view of all the safety mechanisms of the system and where they are placed from a system architecture point of view. We had showed it to you separately, but here we are giving you a consolidated view. Next slide, please.
Yes. So Soumya till now explained what are all the safety mechanisms we consider to make sure we have a sufficient amount of failure mode coverage. So now it's the time for us to convert those safety mechanisms as a requirements and provide it to the further development in part 5 and part 6. So basically this has three broad categories. One is functional requirement, and then safety mechanism related requirement, and then we do have some requirements to be implemented for us to test the features during development and as well during manufacturing. So these three are the broad categories we need to consider while deriving the detailed technical safety requirements. So in the functional safety requirements, we first need to obviously consider the functional safety requirements, which is our main intention to do it at the vehicle level. So we need to consider the functional safety requirement, and then safety related dependencies and constraints. For example, we might have some constraint in monitoring some icon during when it animates. So what are all the constraints we have in a system that needs to be considered while deriving technical safety requirements? The external interfaces of the systems. So it could be a CAN interface, or it could be some other external communication interface. So those related details, what is the message ID, periodicity, what is the value? So those related aspects we need to consider. And the configuration and calibration data. So if our software has some configurable data to be used for a specific functionality, then we need to elaborate what kind of configuration data to be applied for this particular specific use case. And the calibration data, for example, if this is going to be used different kind of vehicle, then we need to go for the feature applicability, or we need to go for some calibration value. So those kind of things, whether that particular use case has, then we need to consider calibration data related things. And as well the other data, something like a regulatory. So if we are using any specific indicator, if that particular indicator has any special requirements into the country which we are delivering, then we need to consider those regulatory related requirements into our TSRs. And then as we all know, we are mostly going for a platform based approach. So in that case, so we need to consider if we have any decisions which is platform oriented, then that has to be taken care. And we are using the safety manuals because the safety compliant micro, when we use it, so we need to adhere to the safety manual requirements. So that has to be considered. And then the functional concepts or other concepts such as cybersecurity. So as cybersecurity not only impacts the privacy, it will also impact the safety. So those kind of safety related aspects coming from functional cybersecurity concepts has to be considered in technical safety side as well, which Nagesh was providing the example of E2E, where masquerading is also part of cybersecurity, and we also consider that here. So that kind of things we need to consider when we derive technical safety requirements. And more importantly, so as we get functional requirements for functional safety specific as well as the product specific from the OEM. So in that case, when we derive technical safety requirement, that should not contradict with our normal non-safety requirements. So it has to be both aligned. So that is one main important thing. And when it comes to the safety mechanisms related requirement, so we need to ensure we have a detailed requirements for each and every safety mechanisms to detect to detect safety mechanisms, or to notify or to control it, or once the fault is detected, how are we going to achieve the safe state? And if we have any degradation strategy, what is the requirement to achieve the degradation strategy? And then if you have any latent fault related requirements, we need to consider that. And main importantly, we need to consider requirement for fault tolerant time interval, which is the main aim of to achieve safety goal within the time interval which we received from OEM, or which we derived on our own in the SUOC base. So we need to consider the fault tolerant time interval. And finally, which Soumya explained, so for hardware diagnostic coverage for the hardware architectural metrics, that as well we need to add into the requirement for the hardware team to use it. And in some cases, we need a special implementation to verify some of the aspects in our system. So that requires some more requirements to detail out how to be implement that particular um, commands to test it. It could be during development, or it could be during manufacturing. So those related requirements we need to elaborate. So with that, we'll be completing the technical safety requirements. And this is a completed version which we can provide it to part 5 and part 6 for the further development. So with that, we'll be completing the technical safety concept aspect, and we'll be going the other parts of part 4, which is mainly the testing. In this, the first one is hardware software integration testing. So basically, we can see that as three things. So if we look at the ISO26262, the hardware software interface or interaction is first originated from systems level. So basically, the systems team, when they prepare the system safety architecture, they are the one going to understand the interaction between hardware and software when they prepare the safety architecture. So there, the HSIS got introduced. And then during hardware development in part 5, the hardware team is going to elaborate with each and every hardware peripherals, electrical data sheet, critical other parameters, their manuals. So everything they will be referring, and then they will be detailing it out, each and every hardware peripherals interfaces which will be used by software. And when it comes to part 6, software side, the software team is going to ensure the hardware signals which is given to software for the usage is correctly provided, and it could be able to used by software team. So those kind of things will be defined and refined in part 4, 5, and 6. So when it comes to testing, the same way we need to verify. So the systems will at the system level will verify the hardware software interactions are working as provided in the system architecture. So we need to verify its functionality and their interaction using technical safety requirements and systems architecture. At hardware level, each and every peripheral, whatever we provided, the interaction and the interfaces to software team is working fine by verifying the hardware peripherals. And there, for example, it could be the input and output of the hardware peripherals. It could be if it is a to D related counts. So the peripheral is providing, the hardware design is providing correct A to D range, and the power up, power down sequences. So those kind of things, hardware team side, they will be verifying. Software side, whatever the interfaces provided by hardware mentioned in the HSI specification, so whether that is correctly provided, and then the correct allocation of ports if it is a multi-core environment, and port direction, whether it is an input port or output port, and the register values, if it is a SPA or a LIN or other CAN related things, what is the baud rate, what is the clock frequency, and main importantly, the power up, power down sequences. So those are all as well verified at the software level. So this is covered as part of hardware software integration testing in part 4. So we just elaborated this has to be provided a tested detail in systems, hardware, and software level. And then we have systems integration testing. So this is we mostly widely used. So there is not except the fault injection testing, which is mainly required for when we introduce a safety mechanism. We need to ensure the safety mechanisms are working fine and the safe states are taken correctly by introducing a fault, and then we'll verify it. So that is one important thing when it comes to safety related system integration testing. The other things are as well, we have to verify the functionality, and then we have to verify the interaction as per the software architecture, safety architecture, and then the interfaces, in external and internal interfaces, which is used inside the system architecture, is correctly implemented. With that, we have come to almost end of the session.
Yeah, thanks, Sridhar and Soumya for the handling the complex topics and giving me the easier ones. But yeah, thank you. So can you go to the last, this next slide, please, Sridhar? So here, yeah, so basically what I'm trying to show here is what are the things that we covered during this presentation, and just a quick mind map of what we mean by all this. So basically, before we even begin the technical safety concept, as I explained, there are certain things that we need to understand. So what are the things that we need to understand is that there are different views of looking at the system. So there is the functional view, there is the system view, there is the data path view. So we need to understand how all these looks. And then there are the key concepts in functional safety, which is the independence, which consists of common cause and cascading. Cascading is the freedom from interference aspect. And then there is the fault tolerant time interval, the FTTI, and as well the fault handling time interval, FHTI. Then the failure in time. So even though I say failure in time, it is actually the hardware metrics, which consists of the failure in time, the single point fault metric, and the latent point fault metric. And then we also have to understand what is meant by Acell decomposition. So once we have this fundamental understanding of these key concepts from the standard, and as well a clear view of how our system is going to look like, the functional view of our ECU, the system view of our ECU, the data path view of our ECU. Once we have that, then we can start looking at the analysis part. So we can start looking at how do I understand what are the ways in which my system can fail. And the analysis of the system could be done using either the Fmea or the FTA. So they are two different ways to perform safety analysis. There are multiple ways in which safety analysis could be done, but here, since the ISO26262 primarily talks about these two analysis techniques, we have explained that. So Fmea is the bottom-up approach, and the FTA is the top-down. And per the standard, FTA is recommended for SLC and D system, and Fmea is used for all the SL levels. So that is the second step. So once you understand the system, and you have to analyze the system. Then once you have analyzed the system, you need to start creating the concept. So basically, when you are starting to create the concept, you need to look at all the aspects that we covered previously, and as well the functional requirements, the system architecture, the safety manuals that are coming for the micro and the peripherals, the data sheets, and as well the manufacturing process. Because as I said, safety is not just restricted to system, hardware or software, but it is an end-to-end system. And so you need to as well think about the manufacturing aspect. So that is how you create the concept. And then finally, once you have created the concept, it is, again, obviously you will implement, and then it comes down to validating whatever you have created. So that is where we talk about the hardware software integration testing, the system integration testing, and finally at the vehicle level. So this is a high level picture of, let's say, the part 4, how things work in the part 4. And the essential aspect that we covered during this presentation is on the creation of a technical safety concept. Yeah. So with that, Yeah, with that, we come to the end of our presentation. So obviously, we'll have time to take up some questions. There are a lot of questions that have come in. So that's very good. And thanks for all the questions, and thanks for your patience in attending this session. So there are way too many questions for us to answer in the next 5 or 10 minutes. So what we'll try to do is we'll consolidate all the questions, and then we'll post all the responses to the questions in our LinkedIn page and as well in our website. So just to reiterate, all of us, myself, Sridhar and Soumya, we could be found in the functionalsafetyfirst.com website. We are running it so that we could share our knowledge, so we could be found there. And as well, we'll be sharing our LinkedIn profiles, so that if you want to connect to us and if you have any questions to ask, please feel free to do that. Over to you, Soumya, for the question and answer.
Yeah, thanks, Nagesh. So yeah, again, let's take 2 or 3 questions in the time left. What is the difference between FFI and DFA? Nagesh, is this something that you want to take?
Sure. So Sridhar, if you can go back to the slide that we made about the dependent failures. Yeah, again, it's a wonderful question, because this is something that people often get. And yeah, so just to simplify, when we talk about the property of independence, it is also called absence of dependent failure. So when we talk about dependent failure analysis, we are ensuring independence, and independence is consisting of 2 aspects. One is the absence of common cause failures, and the other is the absence of cascading failure. And the absence of cascading failures is also called the property of freedom from interference. So independence, or DFA, when we say we do DFA, we have to do FFI plus the analysis of common cause failures. So it's a combination. Dependent failure analysis is FFI plus common cause failures. Yeah.
Yeah, thanks, Nagesh. Then there is a question, is the fit of an element independent of Acell level? Sridhar, do you want to answer this, or I can take this as well?
Yes, fit of the element is independent of Acell level. It's basically depends on the mission profile, and then the characteristics of the element we use.
Yeah, thank you. Then let me take another question. Why do we need a health manager when we have a watchdog in place? The watchdog or the like a hardware watchdog, if we were to imagine it, whether it's a windowed or a non-windowed watchdog, cannot really detect the various possible timing faults in a system. Yeah, I mean, let's say if we are not executing or petting the watchdog at the required time or within the required timeout, whether that's a windowed watchdog that has a lower or a upper threshold, or it's just a normal watchdog with an upper threshold. If it doesn't get petted within that time, it will time out. But let's say your watchdog could be petted, or like your watchdog may not be petted because of a stuck-at issue at software, which can be let's say a stuck-at issue at QM software or Acell software, or it can be any fault. Because the watchdog is not being petted at the required timeout, you cannot say that let's say a safety software is stuck or a QM software, you cannot nail it down until you analyze. So let's say if I'm assuming that, let's say we have a system with many different safety tasks, and we have for safety we have timing requirements, we have FTTI requirements, we have sometimes we have the functional requirements, functional timing requirements. So if we need to meet all this, each of the safety tasks need to run at the configured frequency. If I decide to run a safety task at 10 milliseconds, let's say I would want it to run anywhere between, let's say, 12 to 8 milliseconds or whatever. I would have to define that every safety task needs to run correctly in the required periodicity for me to meet the FTTI requirements. So now this level of detecting whether the safety task is really running at the required frequency or not may or may not be detected by just having a watchdog. So it really depends on the system. But if I imagine a system with a lot of safety tasks with a wide variety of periodicities, and each of them have their own, timing requirements from an architecture point of view, all this complexity cannot be handled by just having a single watchdog. But it may be that in a certain system this is possible. So that's why it's very hard to generalize the response to questions like this. So we would have to consider the nature of the system and the complexity of the safety software. What tasks does it have? Does it have interrupts? And let's say, does it need any deadline monitoring? Like, does something has to execute within a certain time mode? So if it needs those kind of timing faults to be detected, then just having a watchdog will not be sufficient, and we would need to have a health manager to detect the additional timing FFI faults. Okay, yeah. So I think we will stop here because we already exceeded time, and I'm sorry for the additional 2 minutes that we took. We do have many questions, and thanks a lot. As we said, we'll definitely get back to you with the answers of all the questions, and also this PPT and the recording of this webinar. Yeah, thank you. Yeah, thanks a lot, Sridhar and Nagesh, for your support. Yeah, and thanks everybody for participating. We'll close the session now. Thank you.
Thank you.